Hello student, today I am going to teach you about the master's method. The master's method is the method that is used to solve a certain types of recurrence equations or forms and get the complexity of that equation. This is used very commonly used to get the check the complexity of the certain equation which uses the recursive function to solve the problem. For the Master's theorem can apply to the equation which is of the form Tn is equals to a Tn by b plus Fn. Here what we are doing here in this recurrence formulation, we are dividing a problem of size n into a number of subproblems, and each subproblem is of size n by b, and the cost of dividing the n size problem into a number of n by b size problem is equals to Fn. For applying the master theorem, a should be greater than equals to 1 and b should be greater than 1 and f should be asymptotically positive. It means we are dividing a major problem into a number of subproblems with problem size n by b. The cost of dividing these a major problem into smaller subproblems is equals to Fn. So if the equation is in this form, then we can directly apply the directly get the results by deciding that in which particular case this problem is lying. Uh, Basically, to solve a major problem, what we do, we divide the major problem into smaller subproblem, and these problem are generally the same, are solved similarly with the same sequence of steps. So if you can solve one some problem, you can solve the other one also. So this is kind of dividing a problem into divide and conquer approach. So for example, we can understand this with help of a recurrence tree. Here a problem of size n is being divided into a number of subproblem, and each subproblem is of size f n by b size subproblem. N size problem is being divided into a number of n by b size problems. Here may we look weird that how it is possible that we are dividing the n size problem into n by b size problem, and number is not equals to they are not b problems, but instead they are a problem. But here you may consider that there is a problem, and if we keep on dividing the newly gets a problem into further division, or we further divide the problem the same way, then we shall get the subproblem of the size n by b square, and there would be a subproblems of n by b square after dividing the n by b size problem. And this procedure will keep continue till the problem reaches up to the limit where size becomes equals to 1, because as per master theorem, a should be greater than 1 and b should be greater than 1. So when we cannot divide a problem, then we stop at that point, or the step at the we are left with a single element. At that point we stop the process of branching, and at that point this tree ends. So here what we have done, we have divided n size problem into a number of n by b size problem, and each of the n by b size problem has been divided into a subproblems of size n by b square, and so on till we are left with the single element at the leaf node. Now at now we shall compute what will be the cost of dividing the problems into smaller size of problems. Initially the cost of dividing was Fn, because first when we divide, the problem would be equals to Fn. If we divide a Tn size problem into Afn by b, in this last slide, a Tn by b, the cost was Fn. So initially the cost was Fn. After that, when we divide n by b size problem, then the cost would be fn by b for each sub problem. But there are a number of problems, so the cost at the level 1 would be equals to a into f of n by b. Similarly, at the level 2, there would be a cross a or a square number of problems, and each will have take a cost n by b fn by b square. So the total cost would be a square of f into n by b square, right? So what we shall do, this way we have designed a tree, and we have calculated the cost at each level, and we shall add the cost of division at each level, and that will be the total cost of solving the problem, because at last we are left with the single element and that cannot be divided, so that will be the total cost of division. So this tree at each level is being divided into a number of parts, So each problem of becomes the fraction 1 by bth of the previous size. So this here the term where it ends it will be last. The n is divided by b at each level. First level n, then by n by b, then n by b square, and so on. The point at which n by b square become equals to 1, n by b equals raised to power k equals to 1, then this tree stops. So simply we can say that the division is equals to log n base b, because here we can say that n raised to the power h. So here we are branching is equals to b raised to the power h is equals to, for example, you can say that the log 9 base 3 is equals to 2. So 3 raised to the power 2 is equals to 9. Log 9 base 3 is equals to 2. So 3 of is base raised to the b 3 square is equal to 9. So here we can say that b raised to the power h is equals to n. When b raised to the power k become equals to the n, then that would be the value 1. So the height of the tree would be equals to log n by b. So that would be the height of the tree. And now the number of leaves. How many leaves would be there? Because with height, the number of nodes are increasing, and at level 1 it is a raised to the power 1, at level 2 it is a raised to the power 2. Since the height of the tree is equals to a raised to the power h, so the total number of leaves would be equals to a raised to the power h, and here h is equals to log n base b. So the total number of leaves would be equals to n raised to the power log a base b. So height would be equals to log n base b, and the number of the leaves would be equals to n raised to the power log a base b. So we have calculated the number of leaf nodes, and we have got the height of the tree, and we have calculated the cost of division at each level. Now we shall compare that what is greater than the other, the fn with n raised to the power log a base b. Here we shall compare these two, because fn is the cost of division, and that with n raised to the power log a base b, and if fn is equals to o n raised to the power log a base b minus epsilon for some constant epsilon greater than 0, or we can simply say that n raised to the power log b a base b is greater than fn and polynomially larger, where n is the number, and we can say that n raised to the power log a base b minus epsilon as n raised to the power log a base b upon n raised to the power epsilon, means it's polynomially. If fn grows polynomially slower than the n raised to the power log a base b, then we can say that this case goes under the case 1. and the major term, that dominant term, would decide the complexity. So the complexity here would be equals to Tn is equals to, will be determined by the n raised to the power log a base b, because it is a dominant terms and it will dominate the function fn, and the complexity would be decided by the n raised to the power log a base b, right? This was the case 1. Now for with the given tree, we can say that when the weight increases geometrically from the root to the leaves holds a constant fraction of the total weights. In case 1, the weight increases geometrically from the root to the leaves, because here we can say that the problem at the lower level are of smaller size in comparison to the nodes at the higher level. So the uh, weight increases, but their number of problem is increases. So the leaves, basically finally the loads are being divided at the bottom level. So the total load is being divided, the leaves holds a constant fraction of the total weight. So if in that terms the load at the leaf node is equals to n raised to the power log a base b, because n raised to the power, there would be n raised to the power log t1. Finally at the leaf node there would be T1 and total T1 size problem, and there would be n raised to the power log a base b number of problem. So the total load would be equals to theta of n raised to the power log a base b. So okay. So here in the previous example, so we have said that Tn is equal to theta n raised to the power log a base b. Now compare that. Now in Master's theorem there are 3 cases which are decided by comparing the two variables fn and n raised to the power log a base b. Here in case we have just studied the case 1. In case 1, where n raised to the power log a base b was greater than fn, that was the case of fn, and the dominant term decided the complexity, that was equals to theta of n raised to the power log a base b. Now we come to the case 2, where the two terms fn and n raised to the power log a base b grows at similar rate, means both are nearby equal. Then in that situation, fn would be equals to theta of n raised to the power log a base b into log of n, k is the base of log of n. So in that case, Tn would be equals to n raised to the log a base b log n. In second equation, log k plus 1, and you can leave it. In case 2, when we keep on dividing, then the problem, the weight is approximately same on each of the log b n level, because at each level the weight is nearby same at each level, because in this both are going at the same rate, so the number are equally being divided. In the last term, when the n raised to the power log a base b was greater than fn, then leave were the major portion. Like the weight increases geometrically, because in that terms the number of the problem were increasing much faster than the fn. So the weight increases with the increasing levels. So that was majorly determined by the number of leaf node, and that was equals to n raised to the power log a base b. But in case 2, both were equal, so that was equals to log n raised to the power log a base b into log n, because load was divided equally. In the recurrence tree corresponding to the case 1, most of the weight was at the bottom level, but in this case the weight is equally distributed. So or we can say that approximately equally. Then that in that case the complexity would be theta of n raised to the power log a base b into log n. Now the third case of the master's theorem. In third case, we compare Fn with n raised to the power log a base b. Here in this case, the Fn is greater than n raised to the power log a base b, or Fn is equals to omega of n raised to the power log a base b plus epsilon. Means it is polynomially, it grows polynomially faster than n raised to the power log a base b by a factor n raised to the power epsilon, where epsilon is greater than 0. And along with that, another condition should be satisfied if you are applying case 3. If this condition is not satisfied, then you cannot apply the case 3, and that condition is called the regularity condition. The regularity condition is a Fn by b should be less than c Fn for some constant c smaller than 1. Here a Fn by b should be less than c Fn is called the regularity condition. In that situation, the complexity will be determined by the Fn function, and Tn would be equals to theta of Fn. Here in this case, when we analyze the tree, the weight decreases geometrically from the root to the leaves, and in this case, as we moves towards the bottom layer, the weight decreases. So the root holds a constant fraction of the total weights. So here most of the weight is handled by the decreases. So most of the weight is determined at the root level. So the cost in this case would be equals to theta of Fn. Here in all these cases, the complexity has been defined in terms of theta. Okay. So these three are the cases of the master's theorem. The master's theorem, right? Now we shall take few examples to understand the master's theorem. Here in this question, Tn is equals to 4 Tn by 2 plus n. Here a is equals to 4. When we compare this equation with the standard master's method, then here a is equals to 4 and b is equals to 2 and Fn is equals to n. Before solving a question with master's method, first we compare the two functions Fn with n raised to the power log a base b. Here first with Fn. So Fn is equals to n, we have already calculated, and n raised to the power log a base b is equals to n square. Putting the value a is equals to 4 and b, we get the value n square. So in this case, n raised to the power log a base b is equal to n square and Fn is equals to n. Means n raised to the power log a base b is greater than Fn, and it is here epsilon is equals to 1. So definitely it is polynomially larger than the Fn function. So we can easily apply the case 1, and the complexity would be determined by the n raised to the power log a base b. So in this case, Tn would be equals to theta of n square. Now we shall take the second example. Here in the question, Tn is equals to 4 Tn by 2 plus n. Here n a is equals to 4 and b is equals to 2. Then n raised to the power log a base b is equals to n square and Fn is equals to n. Here again n raised to the power log a base b is greater than Fn, and here again epsilon is equals to 1. So Tn would be equals to theta of n square. Now we modify this question. In place of the Fn where the value was n, we are changing the value n square. here fn is equal to n square, and the equation is Tn is equals to 4Tn by 2 plus n square. So here a is equals to 4 and b is equals to 2. So n raised power log a base b is equals to n square, and fn is equals to n square. Fn is equals to n square. So in this case we can see that n raised power log a base b and fn both are equal. When both grows at the same rate, that is the case of case 2, and the complexity would be equal, fn would be equals to n raised power log a base b into log n, and log n, here 0 has been marked, ignore that value, it is log n raised power log a base b into log n. So n raised power log a base b is equals to n square, so Tn would be equals to theta of n square into log n. So this is the case 2. The first question was of case 1, the second question is of case 2. Now the third question. In the third question, Tn is equals to 4Tn by 2 plus n cube. Depending upon the fn function, the question comes into the case 1, case 2 or case 3. Here a is equals to 4 and b is equals to 2. So n raised to the power log a base b is equals to n square, and fn is equals to n cube. Here clearly fn is greater than n raised to the power log a base b, or we can say that fn is equals to omega of n square plus epsilon, because fn is equal to n cube and epsilon is equal to 1. So definitely it's polynomially greater than n raised to the power log a base b. But for declaring a question that it comes under the case 3, we should verify that this satisfies the regularity condition. The regularity condition is a fn by b should be less than c fn for c smaller than 1. So a is equal to 4 fn by b. N by b means n by 2 and n by 2. So fn by b, so fn is equal to n cube. So n by 2 is equal as fn cube is equal to n by 2 cubes is less than c fn. Here fn is equal to n cube, and so f4 of cn by 2 cube should be less than c of n cube. So you may ignore the value of the c, as you could because this is a constant function, so that the variable here is n. So we should decide that what would, depending on the value of n cube would cancel out, and 2 cube is equals to 8. So we can say that c is equals to 1 by c cube by 2, n cube by 2, c is equal to 1 by 2. Here instead of cn by 2 you should write c, but just n by 2 cube. So it's equals, c is equals to, c is equals to 1 by 2. Should be greater than 1. So c lies between 0 and 1. So this satisfies the regularity condition, and this question can be solved using the master method. So Tn would be equals to theta of Fn, because Fn is greater than n raised to the log a base b, and that would be equals to theta of n cube. Now the next question. Tn is equal to 4Tn by 2 plus n square by log n. This is the different question. Take care that here again a is equal to 4 and b is equals to 2. But n raised to the log a base b is equal to n square, but Fn is equal to n square upon log n. We can say that these two values are not polynomially, no one is polynomially greater than or smaller than the other. So in these situations, the regularity condition is not satisfied. Regularity condition is basically to verify that the relation between these two is either polynomially greater or smaller than the other. So in this case, this does not satisfy the regularity conditions, and so Master's theorem cannot be applied. So in this situations, we shall ignore that this question cannot be solved using the master's method. So here I shall give you a brief revision. So the master's theorem is the equation which can apply to the recurrence equations of the form Tn is equal to A Tn by B for value A and B greater than 1 and f should be increased positively. And in this, the height of is equals to log n base b, and the overall number of leaves is equals to n raised power log a base b. Depending upon the question, in sub question, the major cost, the higher level nodes have more weights than the bottom level, and in one case there are different situations, and depending upon the division of weights. In case 1, the major weights lies at the leaf nodes, so the cost would be determined by the leaf nodes, and Tn would be equals to theta of n raised to power log a base b. In this case, n raised to power log a base b is greater than Fn. Then the questions comes under the case 1 category. In case 1 category, the weight increases geometrically from the root to the leaves, and the leaves hold the constant fraction of the total weight. In case 2, the weight is approximately same throughout the tree, and the complexity is equals to theta of n raised to power log a base b into log n. And in case 3, the Fn function is greater than n raised to power log a base b, and the weight decreases geometrically from the root to the leaves. So the cost would be equal to theta of Fn. That's all about the master's theorem, and thank you.